How's it going? My name is Carl Diaz. I'm with the Learning Resources Center here at the University of Colorado, Denver. And today we're going to be talking about concepts associated with simple harmonic motion. Now this will be a two-part video. This is going to just describe the motion in general in terms of the equations and the graphs. The next video will describe actual systems. We'll talk about pendulums and springs specifically and how we can use these equations and apply them directly to these systems, but first we have to understand what's going on. So to start off, right, we want to know what we're talking about, define what we're talking about. So simple harmonic motion, it's important to understand what that is, but it's really just oscillation, right? Vibrations, how things vibrate, oscillate, right? All these different things, right? You can say it a lot of different ways, but that's all we're trying to say, right? And simple harmonic motion is specific because it's systems that oscillate around a stable equilibrium, okay, and that's important. When we talk about stable equilibrium, I could probably draw it over here, right? It's like if we have these two different situations here, and let's say I have a ball here. One of these, right, if I push the ball this way, the ball is going to roll back this way. If I push the ball this way, the ball is going to roll back this way, right? Versus this one, right, they're both sitting still. They're both at an equilibrium point. Versus this one, if I push this ball this way, it's going to go and it's going to keep going, which is an unstable equilibrium. It's sitting in an equilibrium, but it's unstable because it's not going to return back to the equilibrium state. So this type of situation needs to have a stable, this top one, the stable equilibrium, where if I push the system one way, it's going to want to return back to this equilibrium point. Or if I push the system the opposite way, it wants to return to this equilibrium point. Again, if I push this off this hill, it's not going to come back to the equilibrium point unless I push it back. We want it to naturally restore to the equilibrium point, right? And the other condition for oscillation is not only oscillating around that stable equilibrium point that we were just talking about, but it's where the restoring force is proportional to the displacement from that equilibrium, right? These objects, a pendulum and a spring, right, they're going to naturally just sit. When you're not touching them, they're going to naturally sit in a place where they just sit still. No one's touching them, right? And then we can displace, right? I can stretch the spring or pull the pendulum a certain displacement, and that displacement will be proportional to what we're calling this restoring force. Okay, and the restoring force will always be described this way in terms of K, which is what we're going to call a wave number. There's a lot of, it could be, if we're talking about a spring, K could be what we call a spring constant, but K really is a wave number, which it's describing how the system's going to oscillate. So K is very important, but it can vary based off the system. Like K here, we have to derive a totally different K because we really look at K as, you know, some sort of thing associated with like a spring constant. We'll talk about that here in a second. Okay, so again, that's the idea. Simple harmonic motion is just trying to describe oscillation or vibrations, right? And these oscillations or vibrations happen around a stable equilibrium point, right? And the restoring force is proportional, right? Proportional. This is the displacement from equilibrium point. That restoring force is proportional to that displacement from equilibrium, and in this case by K. Okay. So when we look at these two systems, we got to not only be able to describe certain points on them, but we also got to be able to describe them in terms of a graph, right, and in terms of equations as well, right? So like I said, when the system's just sitting still, no matter if it's a pendulum, right, or a spring, they're going to sit, and where they sit naturally at rest is what we're going to call the equilibrium point. Okay, that will be the equilibrium point. If you want to see the equilibrium point for a system, let it sit at rest. Wherever it sits at rest, it is an equilibrium. And that's why, for example, you know, a ball, when you bounce it on the ground, that's not in simple harmonic motion. Why? Because it's not sitting around a stable equilibrium point. You'd be like, well, how do you know that? Well, where's the ball's equilibrium point? If I let go of the ball, it wants to naturally sit where? On the ground. Well, the ball isn't oscillating around the ground, right? It bounces up from the ground. So the ground, right, even though it would be considered its equilibrium point, it's not oscillating around that equilibrium point. So it's not necessarily considered simple harmonic motion, okay, like a bouncing ball, right? It's these systems where they have this equilibrium point where they naturally sit at, and then when they're displaced or when they oscillate around that equilibrium point, right? The spring goes back and forth. Here's the equilibrium point, but the spring moves here and here, right? It oscillates around that equilibrium point, or the pendulum, right? It oscillates around, right, the equilibrium point. All right, and that's what we're trying to describe here with both these systems. All right, so when they sit at rest at their equilibrium point, there's no displacement. That x in this restoring force is 0, right? And if there's no displacement, there's no force, and if there's no force, there's no acceleration. So when they sit naturally at equilibrium, this is what they kind of look like. I mean, obviously the graph wouldn't have anything on it, right? The graphs would be 0, and these are 0, or just sitting at equilibrium, okay? But now what we want to do, right, is instead of thinking this as sitting still, we want to think about it as it oscillates. Think about this system in terms of it actually oscillating, right? So we want to think of this not being at rest now, but these are just snapshots of this system oscillating, either like this, right, or like this, right, like a spring. So these are now, again, snapshots, okay? So if the thing's oscillating, okay, if the thing's oscillating and we take its first, so this thing, both of these things are oscillating right now, right? They've already been started, we already got them starting oscillating, so we're watching them oscillate, right? And they oscillate like this. They're going to come over here, come back to equilibrium, come over here, come back to equilibrium, come over here, come back to equilibrium, right? Which is really just this, okay? So when we start here, right, at equilibrium, again, these are moving, even though it looks like they're staying still, and we just said that that's resting point. We're now saying these things are moving. So, right, they just moved from this point back to here. So they just got back to their equilibrium point, okay? And we can say a few things about this point. When they get to their equilibrium point, it's just whatever we said when it was sitting rest is still true. The force, the restoring force at equilibrium point, even when it's oscillating or moving, is 0. And if that restoring force is 0, so is acceleration. And again, the displacement from equilibrium point is 0, even when it's oscillating, when it reaches that equilibrium point. But there's something that we know, and we can kind of see from this next graph, is that when this system's oscillating, okay, and it reaches its equilibrium point, it actually has a max velocity. So we can't see it on these graphs, but this graph would start up here, right, with some max velocity, where, right, we started where x was 0, right, but when we get back to where x is 0, v velocity is going to be max, okay, for both of these. Okay, again, if we're oscillating, if we're staying still, then remember, v is 0, but if we're oscillating, if we just came from over here, and we come back to our equilibrium point, when we reach that equilibrium point, the restoring force and oscillation is going to go, and acceleration is going to go away, but the velocity will be max at that point. Okay, it can't go any faster than when it's oscillating than when it reaches its equilibrium point. So when these objects in simple harmonic motion reach their equilibrium point, when they're oscillating, they will be moving at max velocity. That's something to remember. We're going to talk about it over here. Okay, I'm just trying to get you ready for things, all right? So these systems are here, right? And then they swing, right? This is going to swing over here. This is going to move, right? Have some displacement, right? This is going to swing this way. And when they reach a certain point where they're going to stop for just a second before they start to head back in the other direction, right? That's the next snapshot we want to take, right? And we want to say at that snapshot, when they're at their max displacement, that x is max. And what it also is when we talk about those equations will also be the amplitude. When that's max, okay, that means acceleration and restoring force will also be max, okay? So when x is max, restoring force is max, and that should be true because we said the restoring force should be proportional to displacement, okay? So when x is max, f is max, okay? And so is acceleration, all right? And when all these are max, right, if it's at a point where it's stopped and it's getting ready to head back, when force, displacement, and acceleration are max, velocity will be 0. Okay, so again, restoring force, if you can't see it over there, acceleration and displacement. These will all be max. And when these are all max, velocity 0, okay? And then look up here what we just talked about. So when these are all 0, velocity's max. They kind of play off of each other, all right? So again, the snapshot we're looking at is when the pendulum's all the way over here, or the box is all the way over here, and it's getting ready. It's stopped, but just for a second, because it's going to head back, right? These things are oscillating, like this, okay? So when we take our next snapshot is when it makes it back to equilibrium, right? When it makes it back to equilibrium, again, we've already described that point. That's where the restoring force will be 0. And if restoring force is 0, that means the acceleration will be 0. And also displacement will be 0. But at that point, when the box gets back to that point, that will be again at its max velocity. Remember, we said every time that box reaches its equilibrium point, if it's in oscillation, it will be at its max velocity, okay? And again, that's true for a pendulum or a spring mass system, okay? And then again, our next snapshot is going to be when they're all the way over here. So again, they've stopped and they're getting ready to head back now in this direction, okay? So both the pendulum is over here and the spring is over here. This has max compression, right? Or this is the max distance it's going to make it over here, right? And again, that x is also going to be the amplitude. We'll talk about that. All right, and at that point where they're stopped, v will be 0, velocity will be 0, okay, where it's stopped for both of these, but where velocity is 0, restoring force, acceleration, and displacement are max, just like here, okay? And remember, this is true for both things, right? For over here, I could write if I wanted to, right, that velocity is going to be 0 at this point. The restoring force, acceleration, and displacement, these are all going to be max. But when I get here, it's opposite, right? I see that the restoring force, displacement, and acceleration are all 0, but now velocity is max. So they go back and forth. We just went from max restoring force, acceleration, and displacement to 0, right? So every time we're at equilibrium, we see that the restoring force, the displacement in the restoring force, and the acceleration, right, or the rate of change of motion in these objects will all be 0 every time we're at equilibrium. And we see every time we're furthest from equilibrium, right, we see that the restoring force, acceleration, and displacement will be max, but velocity will be 0. Okay, that's the thing to see here, all right? And again, you can notice how this thing's oscillating. And again, when it gets over here, we can say the same thing that we did up here. We're both restoring force, and this is for both systems, right? Acceleration and displacement. These are all going to be max, and velocity is going to be 0. Max compression, or at the max point that this pendulum moves over here right before it gets ready to head back, okay? So that's important that you understand these snapshots and what's going on, because we want to graph the motion of these objects, okay? And in order to graph them, we got to have some idea what their values are doing, because these graphs are telling us the values of what's happening over here, okay? So again, so like we're imagining, right, that this thing's already oscillating, we're at an equilibrium point, and the thing, right, and we want to graph this now. We want to graph what these systems look like, whether it's a spring or a pendulum. What we want to graph, the first bit of motion where it goes from equilibrium point. Again, these things are already oscillating. I'm not starting it to oscillate, okay? Where they go from equilibrium point to some max displacement, okay? So when we're here, we're at equilibrium point. This is max displacement right here. When we come back here, this is equilibrium point. And then down here is max displacement again. Okay, so we want to graph this motion as it goes from equilibrium to max displacement to equilibrium to max displacement. We want to graph that motion, okay? So when we're starting at equilibrium, all these are kind of 0. We can't really see what's going on, but we know that the velocity is max there, so we know it's going to be starting up here. That's what I'm kind of trying to indicate. And then when we move from this equilibrium point to our max displacement, right, both these are going to move over here, which is this snapshot, right? That means that the displacement, right, is now at its max. So it's gone from 0, right? If if we're at equilibrium point, that displacement's 0, and it's gone to its max value, so it should plateau out because it can't go any further, right? Meanwhile, we know that when we get to that max displacement in either one of these, velocity is going to be 0, right? But we knew velocity was max at equilibrium, so we know when we come from this point to this one, we know velocity is going to be going from some max value to some minimum value, or 0. Again, I marked on here, right? All these lines right here mean 0 value. So this is 0 displacement, this is 0 velocity, this is 0 acceleration. So when you're at that point, you're saying 0 for whatever this value is. If velocity is 0, okay, furthest from equilibrium, then that's what this graph should show. Okay? Meanwhile, displacement, right, we said when we're furthest from equilibrium, we said both displacement and acceleration, right, are going to be some max value. Displacement is this. And again, we moved in the positive x value. Okay, so this way. And acceleration, right, we know that if we're looking at this, right, we know, as you can see, I'll use this as an example. I'll draw it a little bit bigger. Right, acceleration is this way. It's the same direction as net force, but our displacement, right, the box moved this way, right? So displacement and acceleration, no matter if we're on this side of the equilibrium point or we're on this side of the equilibrium point, displacement and acceleration will always be opposite. Okay, see here, down here, when we're on the other side of equilibrium, acceleration is going to be now this way, but our displacement, right, we're moving this way. Our displacement is going to be that way, right? So they're always opposite. And so that's what we got to indicate, right? If acceleration has a negative slope, right, or it's going to be opposite, it's going to be the opposite direction of displacement, we need to indicate that on the graph. So even though x looks like it's increasing, a looks like it's going down to the negative, a still increasing, right? It just has a negative slope in comparison to the displacement, right? Because displacement's a positive. We labeled this as, probably shouldn't have made that clear, but on all these I labeled this positive x on this side for both these systems. This side is positive x. So when they move this way, we're moving in the positive x direction. When we move this way, we're moving in the negative. Okay, so we just want to make sure that we indicate that on our graphs when we're drawing. Okay, so when we're furthest from displacement, our displacement graph better have a max value. Our velocity better have a 0 value because the max displacement velocity is 0, and our acceleration better have a max value, but an opposite slope of displacement because they're always opposite of each other. Okay? Now, our next snapshot is when these systems again return to equilibrium. We know when they return to equilibrium, the net force, acceleration, and displacement will be 0. So we see that we go from this graph to this one, where displacement went from some max to now 0. X is 0, and that's what we said. At equilibrium, x will be 0. So that's what the graph should look like. Meanwhile, velocity now that we're at equilibrium, we know velocity should be max. So velocity went from some 0 value to some maximum value, right? And then we have over here that acceleration, right? Now it went back to 0. Right, acceleration we said is 0 at equilibrium, and so it's went from some max value to now 0. All right, now we're going to talk about these equations in a second. Don't worry, we will get to them. Just hang tight. All right, and then for the last part, right, where the pendulum now moves from equilibrium and does a full, right, reaches its max displacement point on the left side, right? We did max displacement on the right side, which is what this is. Now we want to do max displacement on this side, where both the pendulum or the box are all the way over here. They're stopped, but they're getting ready to head back in this direction, right? So we know for that, when we're at max displacement, x better go from 0, or at equilibrium, x is 0, to some max value. So we see the graph go from 0, x is 0, to some max value, where x is max here, right? We see that at equilibrium, or furthest from equilibrium, we know velocity is 0. So we went from velocity, when we were at equilibrium, velocity had some value, to when we're furthest from equilibrium, velocity is now back at 0. And then again, acceleration, right, is max furthest from displacement, but it's opposite of displacement. So here, displacement's now negative and acceleration's positive, but they both have max values because furthest from displacement, both x and acceleration should be max, and that's what these are showing, okay? So that's how you kind of graph these, right, bit by bit, looking at the situation, right? So over here, right, as we start to move from equilibrium, right, over this way, this is going to increase, right? And then as we move back to equilibrium, this is going to decrease, right? And then as we move back away from equilibrium, it's going to move away from equilibrium again, okay? So that's what this is going to show. All right? And then when you have a full graph, if you're just watching one of these, right, if you're not making it bit by bit, if you're not trying to look at the snapshots that we were trying to look at, and you just want to see, you're just watching something oscillate and you're graphing it, this is what it's going to end up looking like, right? Where, right, as displacement increases, velocity decreases, right? And then as velocity increases, displacement decreases, which is what we were saying down here, right? And the same thing here is displacement increases, so should acceleration, but in the opposite way. And then as displacement decreases or comes back to equilibrium, so does acceleration. All right, so not only, I know down here we indicated this value is 0, but also know that when you reach this point, that is equilibrium point for these systems, okay? So every time you get back here, so when you come up and then come back here, you're at equilibrium point. When you're here and come here, you're at equilibrium point. Oh, I'm sorry, I'm so sorry. That's not correct for that. Every time you're up here, I wrote that wrong. It's for the displacement acceleration, every time you're here, you're at equilibrium point. Every time you're at some max value, make sure I say that right. Every time you're at some max value for velocity, you're at equilibrium point, and every time you make it back to this line on the acceleration displacement graph, that's when you're reaching equilibrium point. It's important to know that, right? So we know that as we start to move away from equilibrium point, right, velocity decreases, right? So we knew that at equilibrium point, velocity was max. Again, you want to label these up just to have some idea of what's going on, but things should correlate. So make sure that you're looking at this, looking at how we built the pieces, and seeing how these go together with this, because you want to see how they work, right? And then if we want to write equations for this wave, right, we're just watching it, right? And we want to write an equation for the displacement of the box or the pendulum from equilibrium, the velocity of the box or the pendulum, or the acceleration of the box or the pendulum. We can do it this way at any time. So these equations are describing any time. If I wanted to know where, where the box was at 3 seconds, right? I could find out where the box is at 3 seconds. Right here's the time for all these. So if I wanted to know where the box was at 3 seconds, I can put 3 seconds into here, right? And omega, right? I would know omega. Omega would be given to me, and we'll talk about that. That's what the second video is about, okay, is to try to describe omega in here, because omega is going to kind of fluctuate based off the system, okay? But you'll know your omega, you'll be able to put it in there, and omega will typically, sometimes it'll just be omega, sometimes it'll be frequency. But the thing, since these are all a function of time, right, you can write all three of these equations. Every variable is going to have a number except t, and then t is the thing that varies, right? So that's where we could say t could be 3 seconds, t could be 5 seconds, okay? So we could look at the displacement at any time, the velocity at any time, or the acceleration at any time using these equations, okay? If you want to know the acceleration of the box, and after 20 seconds, right, and you know omega and the amplitude, you put the t as 20 seconds, and you're going to get a number, and that's going to be your acceleration after 20 seconds, okay? So you're going to have, when you go to, because they're going to ask you to write these equations, okay? When you go to write them, there's going to be a number for A, there's going to be a number for omega, and all of these, the only thing that will not have a number in these equations will be t. T will be variable, don't put t in, but some, omega and A will have values in all these equations, all right? If you have to write them as a function of time in terms of someplace. But the thing is that we also know at certain points, right, we have max acceleration, right? We have max displacement. So these equations kind of shift when we're just looking at the maximum values, right? We know that this part over here is the function, right? And if we're looking at max values, if we're trying to look at just this point, right? Or if we're just trying to look at this point, which is the max of velocity, right? We're just trying to look at this point, that max point. Well, then they don't have any, this function goes away. And all that we're left with is just that, is just the amplitude. The cosine, right, the trig function, the sine omega t, cosine omega t, those all go away at those maximum points, whether it's up here or down here. And all we're left with are the amplitudes, right? So x max is just equal to a max, right? And this is a. But it's also x, right? So the amplitude is also the max displacement, right? That's what that's trying to say. Velocity, right, is going to be the max amplitude times omega. You don't need this function because at these max points, or even the minimum points where they'll be 0, you don't need this function, and that's what we're doing over here. All right, so let's kind of put the pieces together, right? We said that when the box is furthest from equilibrium point, x is going to be max, and acceleration is going to be max, right? So that's how we start this, okay? Like I said, we don't need to write omega t. We could start with omega t, but we know at that max point, omega t goes away, sine omega t goes away, and all we're left with is a. So that's how we can write it. We know that x max, should have put that in there, is equal to a max, or the max amplitude. That's what that's telling us, right? Or another way to write it is x max is equal to x, because x is a. This displacement from equilibrium is the amplitude. So we can write a in terms of x, okay? That's not so crucial here, but it's important when we go to plug it in other places, all right? Now, we know at this point right here that velocity is 0, so you can just write velocity 0. It has no function, but, let's say, just keep in mind, if you were trying to describe velocity any point in between here, so not at this max point and not at this min point, if you needed to describe velocity anywhere in here, that's what this equation's for, okay? All right? So keep that in mind. But if you need max velocity, we're going to talk about what the equation for max velocity looks like here in a second, okay? But if you need to describe, remember, listen to what I'm saying. If you got to describe any point in between here, that's what this is for. If you got to describe any point in between here, not this max or min value, but any point in between here, that's what this equation's for. Any point in between here, that's what this equation's for. But these max and min values can be described without a function, and that's what you should be knowing here, and what you should be doing. So we know at max displacement, velocity is 0, so we can just write velocity 0, right? But we also know at max displacement, again, all the things we talked about, at max displacement, acceleration is also max. Displacement and acceleration are max. But we know acceleration is opposite, so it's going to have an opposite slope, which means when we write it, the equation for acceleration, we need to start it with a negative sign because it's going to have a negative slope. We need to indicate that it's opposite of displacement. Okay, but again, just like with everything else, at that max point right there, for acceleration, that trig function falls off, and acceleration is just equal to amplitude times omega t. But we know that amplitude can be equal to x, right? So we can write this equation two ways. All right, if we're trying to describe the max acceleration in terms of equation, in terms of an equation, which is the max displacement from equilibrium, this is the equation you use, and it's the what we're trying to say here, the amplitude times omega squared. All right, so it's negative acceleration max as a function of time is equal to the amplitude times omega squared. That's one way to see the acceleration. Or you can change amplitude to x, and that makes this a little bit more functional for what we're going to do in the next video. And we can look at max acceleration in terms of displacement from equilibrium, max displacement from equilibrium times omega squared, okay? And again, omega is just the frequency. We're just trying to describe the frequency there. It's describing the frequency, or how fast or slow the thing's oscillating. So that's why omega is in there. We don't get into those details too much, but just don't forget that. Okay, so again, we're at max displacement from equilibrium. X is max, or displacement's max, but displacement can be just written in terms of amplitude or just displacement from equilibrium. Okay, and if that's true, anywhere we have amplitude, we can exchange for X, or displacement from equilibrium. So we also know at furthest displacement from equilibrium, velocity is 0. But we also know acceleration's max, so we can write that again two ways without the trig function, right? Which means that it can be written in terms of amplitude. Acceleration max can be written in terms of amplitude and omega squared, or acceleration max can be written in terms of max displacement from equilibrium and times omega squared. Either way, they're saying the same thing, but just know that's how you describe, that's how you write max acceleration for an oscillating system. That's the equation. You gotta say that in your head. You gotta remember this, because this is a very important equation. It's a point of reference that we can use. Maximum and minimum points are points of reference that we can use. Okay, so keep that in mind. All right, so then what do, right? The system comes back to equilibrium, right? And we said when we come back to equilibrium, the force and acceleration displacement are 0, but velocity is max, right? So we can see that displacement goes from a max to a 0, acceleration goes from a max to a 0, which is what it should be doing, right, at equilibrium. When it gets back to equilibrium, should be 0. But velocity should go from some minimum point to some maximum point, and that's exactly what we see, okay? So again, when the system comes from as far as it can move and it comes back to equilibrium, it'll be moving at max velocity. And that max velocity will be determined by how far you chose to pull it from equilibrium. Okay, so if I only pull it 3 meters, right, that's going to dictate how fast it gets to equilibrium point, versus if I pull it 5 meters, right, it will be moving faster at equilibrium point if I pull it 5 meters versus 3 meters. Okay, and that's what we're trying to say. But either way, whether you stretch it to 3 meters or 5 meters, in either case, 3 meters would be the max displacement in that case, and if you chose to pull it to 5, then 5 meters would be the max displacement, right? Those displacements from equilibrium are dictating how fast it'll be moving when it gets back to equilibrium, and that's what we're saying, okay? So when the system gets back to equilibrium, the velocity will be max, okay? And again, what that means is that that trig function totally drops off, and we see that velocity, right, when it's maxed out, can be written as amplitude times omega, right? But we know that every time we see amplitude, we can write amplitude in terms of displacement from equilibrium. So we know max velocity can either be written as max amplitude times omega, or it can be written as max displacement times omega. Now you may be asking yourself, Carl, max displacement, when it gets back to equilibrium, you just said x was 0. So if I put 0 in there, doesn't that make velocity 0? No. We're saying that whatever number you put in there is going to be the displacement that you pulled, right? So that's going to dictate the velocity. So if you displace the spring 3 meters, you put 3 meters in there, because when it gets back to equilibrium, that 3 meters, when you multiply it by omega, is going to tell you how fast it'll be moving when it reaches that point, when it gets back to equilibrium. So this is the max velocity at equilibrium, and it's dictated by how far you pull it away from equilibrium. That's what this equation is telling you, okay? So don't think that velocity is 0 at equilibrium. It's not. Velocity is whatever speed it is based off how far you pulled it from equilibrium. That's what this equation is trying to tell you, okay? And again, we know acceleration and displacement are 0, so those are just 0. And then, right, this system moves from equilibrium, where we're at here, away from equilibrium and gets max displacement in the other direction. So now displacement should go from a minimum point to a maximum point. Velocity should go from a maximum point to a minimum point, because we know at max displacement velocity is 0. And then we know that acceleration should be max, so it should go from a 0 point to a maximum point, and that's what we see. Okay, so again, right, displacement acceleration should be max from equilibrium. Velocity should be 0 at equilibrium. Displacement and acceleration should be max furthest from equilibrium, and velocity should be 0 furthest from equilibrium, right? And then acceleration and displacement should be 0 when we're at equilibrium, where velocity will be max, okay? And just like up here, the equations don't change when we're at max, right? X is equal to max amplitude, right? The same thing as up here. And acceleration, now acceleration has a positive slope, and x has a negative slope, so x is negative here. The only reason why it's negative, just remember, is because it has a negative slope. Over here it had a positive slope, so it was positive. That's just indicating direction of slope, okay? That's sine. Acceleration here has a positive slope, so now acceleration, even though it was negative up here, isn't negative down here. The important thing is acceleration and displacement are always opposite sides, okay? But it's written the same way. We know acceleration when it's max, this function drops off, it's just acceleration, or amplitude times omega squared, or more importantly, the max acceleration furthest from equilibrium is going to be the max displacement from equilibrium times omega squared, right? There's two ways to write it, but they're all saying the same thing, all right? So study that, look at that. It's really important that you understand this, because in the next video, we're going to use these equations, okay, to describe these two systems. We already now have an equation for max acceleration. I can write max acceleration for this spring or this pendulum. How? Right there, that's it. That's it. That's the acceleration equation. If someone said, hey, what's the value of acceleration for the spring when it's at max displacement? That! And whatever they tell you what's the value for acceleration when it's 3 meters from displacement, from equilibrium, well then you put 3 meters in there, whatever omega is, you put that in, you'll get a number for acceleration, okay? So this acceleration, this velocity, and this displacement equation, okay, they describe the maximum points of both a spring mass system, or some, a box attached to a spring or something, and a pendulum. These are the generic equations. Now they're going to function a little bit different based off the way that these things oscillate. Omega is a little bit different for both of these. We got to get kind of a new omega. But either way, no matter what the omega is, this describes max acceleration for both these systems. This describes max velocity for both these systems. And this describes max displacement for both these systems. Every time, doesn't matter what's going on. That's the equation for it. And again, if you have to describe the displacement or velocity to acceleration at any other time besides the maximum points, this is the equation you use, okay? Now, if we were to watch these pendulums oscillate for a long time, or this spring oscillate for a long time, this wave would generate, and it would just keep generating, right? Go and go and go. And that's something that we consider a moving wave. Another type of moving wave that you could think of is like water, right? Or like when you splash water, the waves move, right? Or another type of moving wave would be sound, right? These types of things. But either way, when we got to describe a moving wave, a wave that's moving like this, right? And waves can move to the left, right? Or to the right. And again, I don't want you to think we made a left turn here, okay? These oscillating systems, once they oscillate for a while, they start to create a moving wave, right? The displacement is going to be kind of, forming. I guess it's not necessarily moving, I guess, but I shouldn't say that. But it's going to be forming somewhat of a moving wave, right? So we got to be able to describe moving waves, right? How do we describe a wave that's moving, okay? This is how we describe these waves forming in terms of motion. But what if this was like a moving wave, like on water? This is how we describe it. Now, you don't have to know how to derive these. Trust me, there's a derivation here. You don't have to know how to derive these for the algebra-based, but for the algebra-based college class. But you do have to understand them, okay? So, as you know, cosine and sine, right? Cosine is just where it starts at a max value. Sine is where it starts at a minimum value, so that's how those work in there, right? We're describing these as a function of y, right? Y, the height of this wave is being described, as a function of x and t. I said that incorrectly, right? So these moving waves, when we describe them, we're describing how high they're going to go, but it's going to be dictated by their linear movement, okay? And that's what this is saying. So their height is going to be a function of x and t, all right? And either one of these equations, whether it's starting at max or min, is going to have the same variables inside these brackets where it's going to be omega t plus or minus kx, okay? And either way, whether it's sine or cosine, it'll be omega t plus or minus kx, all right? And that those plus or minus signs mean something, all right? So when this sign is positive, or when x is positive, so when this sign is positive, x will be positive, right? That means the wave is moving to the left. So it's kind of opposite, right? We would think positive x, well, if that was positive x, wouldn't the wave be moving that way? No. If it says positive x, it's moving in the negative x direction, okay? And if this says negative x, right? When x is negative, the wave is moving to the right. Okay, so just think opposite, okay? When x is positive, that means the wave is moving in the negative x direction. When x is negative, that means the wave is moving in the positive x direction, okay? Or left or right, you can think of that either way, right? Moving to the right, or positive x, moving to the left, or negative x. It's another way to think of it, okay? But just know how to read these equations because you need to fill everything in. Again, k is going to be the wave number, okay? You need to know that. Omega is going to be what? Angular frequency, okay? T and x, just like we said over here with t, they're going to vary, so they're not going to have numbers when you write this equation. K will have a number, omega will have a number, okay? But this functions as a function of x and t, so x and t will just kind of stay what they are in this equation. But if you need to write it out, if we say write an equation for a moving wave, amplitude, omega, and k need to all have numbers in here, okay? And then if they say the wave's moving to the left, this better be positive x. And if they say the wave's moving to the right, this better be negative, okay? It's not plus or minus. It's either plus or minus based off the way it's moving, okay? All right, and the other thing is that when two moving waves interact, okay, so let's say we see this red wave right here, that's a big wave. Let's say that that wave was moving this way. And this blue wave right here, right, we see it has a higher frequency. Let's say it's moving this way. When these two waves interact with each other, or they could be moving the same way and interacting, but let's say that they're interacting with each other this way. They're going to combine, and we're going to get something called constructive and deconstructive interference, where every time their max points meet, we're going to have a maximum point. Every time their max points are opposite, we're going to have a 0 point. And that's what constructive and deconstructive interference is. Even though this wave might be max here and this wave might be max here, the resulting wave, when we add these two waves together, those are going to cancel each other out. So we see, right, like right at this spot, that they're 0. See that? Because they canceled themselves out. Where here, right, they're both at some maximum point, so we got a maximum value there, okay? So, the point, you want to understand constructive and deconstructive interference, right? So constructive interference is where they're additive. Deconstructive is where they, where they're opposite of each other and you end up with nothing, right? But at the end of the day, if you want to just describe this wave, this resulting wave, these two waves are going to interact and give you this resulting orange wave, you can just write that wave using this equation. Okay, you can describe this wave, again, as why we're writing as a function of x and t, but here it's 2 times the amplitude cosine of omega t, okay, and that's all multiplied by sine kx. Now again, you don't have to know how to derive this, that's why it's not on here, but just like up here, you need to know what needs numbers. So everything in this equation is going to have numbers except what? X and t, that's what you know. So amplitude needs to have a number, omega needs to have a number, or what we call angular frequency, k needs to have a number, or what we call the wave number, but x and t will remain with no value. We'll just write them as x and t in here because it's going to function. And then we can say, hey, when this wave's 2 meters away, right, and at 3 seconds, how high is it going to be? That's one way we can see the amplitude, because y is looking at how high. But again, we're really just going to want you to write the equation to describe this wave. So you're going to be writing this as a blank slate and then filling in amplitude, omega, and k. Just like up here, you're going to either write this in terms of sine or cosine, right? And then you're going to fill in omega and k and amplitude in terms of numbers, okay? All right, well, I hope that was helpful. I know this was a little lengthy, but I hope that was helpful. Again, this is paired with the second video, so after this one, you need to go watch the video where I'm going to talk about pendulums and springs, but we're going to look at them very specifically. We're going to write equations for max acceleration, max displacement, all these things specific for a spring and specific for a pendulum, because we want to see what's exactly causing them to oscillate, and we'll also look at, because of their oscillation, we can look at their period and things like this, like the time it takes them to make a full oscillation. So I hope this was helpful. I'm super proud of you. You're almost finished with physics, so keep going at it. You only got a few more weeks left. Just work at it hard. These last few things are kind of tricky, but just push through them, okay? I know you can do it. I'm super proud of you, and I'll see you on the next video.